An example I want to show you here. We have three variables here, x1, x2, x3. They are created on purpose to be collinear, to have high correlation with each other and with dependent variable y. The correlation matrix, when we look at that, you see 0.98. x1 is almost a copy of x2. You see 0.99. x2 is almost a copy of y. You see others are okay. So 0.98 and 0.99 show from this correlation matrix, we see that x1, x2 got a problem. If we use least square solution for the data that we have as it is, without paying attention to collinearity problem, the result looks like this. Intercept, regular, you want to look at this LS coefficient, least square coefficient. Intercept 0.22, x1 minus 0.4, x2 2.42. And to see if the coefficients are having some kind of goodness in them, we go to their standard error. In the beginning, I explained what is the standard error that let us determine the amount of error, how much wrong we can go with the sample data. In the confidence bound, I explained. So for x1, this can go 1.094 wrong. The standard error is too high. For x2, 2.42 is the coefficient, but this coefficient can be as wrong as plus minus 1.09. Is this reliable? x3 is minus 0.47, but it can go wrong as much as 0.83. A coefficient that can go wrong as much as plus or minus 1, is it reliable coefficient? You will ask. And when this kind of standard error you see in the regression problem, coefficients are here, but looking at the coefficient is not the only thing. They are only usable if the error they can cause is little. This much standard error means we cannot rely on this model. Why? Because multicollinearity. Shall I take a pause and let you think? After we appreciate the problem, there are solutions, but knowing this kind of problem can occur is more important. We will think about solutions, but if we understand multicollinearity, looking at this is one way of looking at or detecting multicollinearity, looking at the correlation matrix. There are other ways. I will explain how. But to keep things connected to regression, let's look at the correlation matrix. And here we see, oh, these numbers are going to cause trouble. And yes, if we do standard regular least square coefficients, these are producing the smallest squares, smallest red boxes, smallest errors. These are the least square solution, the best possible error, but standard error is too high. They are not reliable. Now you mentioned standardization, regularization. One way to overcome this multicollinearity problem is regularization. The other way is to get rid of multicollinearity from the data. We will look at that in a future session. How do we do that? But today, for regression, what can we do for multicollinearity? You see, there are some columns, regular ridge coefficients. I didn't touch them yet, but just notice these coefficients have very small standard error. We are very much confident about the value of x1 and x2, right? And we also have standardized ridge coefficient, and for that we have appreciate how putting ridge in the equation, we have drastically different coefficients for x1 and x2 compared to standard regular one. Not only that, we have very small standard error. That's good. How do we do that? All right, what do we do to address multicollinearity? It's called ridge regression. I will explain the nomenclature. Why is it called ridge regression? But what is it? It's just treating the error differently. This is the error caused by W's coefficients. We know, we agree, we are going to use sum of squares. Okay. Other than this, if we add this component to our error function, we are having W's squared and summed, L2 norm of W. If we take L2 norm of W's, it's going to force the algorithm, the iterative least squares algorithm, to think of error. Error is here. Even if error is very small, the algorithm will not converge because large number of W's will add to that error and force the algorithm to find a constrained solution that is not only looking at reducing the error, but as well as having some sensible W's geometrically. If this is the error function, this is the best point. Your algorithm wants to go there. Iterative least squares want to go there, but you restrict it to this area. You say the only feasible solution I want will be in this area. So even though least square, the minimum of global minimum of the error function is here, you will get this solution. And thus, through this constraint, through this regularization of the error function, you will make sure that your regression coefficients don't get carried away by only the error, but they are sensible coefficients. They will have smaller standard error. Analytically, if we represent, you see the same error function, but here instead of x's, we are using z's. Z's are the standardized x's. We minus from each feature the mean of that feature and divide it by the standard deviation. We normalize. We call them z's, and rest of the thing is same as we saw in the error function analytic solution of standard least square. But we are adding lambda multiplied by W transpose W, which is L2 norm of W. W's are the coefficients. Same thing. We are adding that to the error function. So taking the gradient or derivative of the lambdas, the lambda multiplied by W's, as well as the error itself, shall give us the analytic solution. When we solve it the same way we solved the equation and reached to the normal equation in least squares, this is very much similar to the normal equation, except this lambda multiplied by identity matrix. If you remember, identity matrix is all zeros except ones on the diagonal, right? Identity matrix size is same as Z, m by m. And then you multiply lambda with that. So lambda here, I didn't mention, it's again a heuristic number. You want to experiment and find out which lambda works best. 0 lambda means you don't want any penalty, you don't want any regularization. Higher the lambda values, more the penalty for having larger W's, more the regularization. So it will be a heuristic number dependent on the problem. For every problem, you will explore with a range of lambda values, which one works best through cross validation. But let's say we found that lambda one, 0.002 is the best one. So we are multiplying that 0.002 to identity matrix and adding that to Z transpose Z, which means we are adding a small number, lambda, to the diagonal of correlation matrix. If you want to visualize that, Z transpose Z is the correlation matrix of normalized data. The diagonal of that matrix are the autocorrelation values. We add lambda to each of those values, taking inverse, and rest of the thing is same as our normal equation. All we are trying to do here is add some regularization to the diagonal components. That's why we call it ridge. That diagonal is the ridge. So look at the correlation matrix is kind of symmetric, right? X11 is X12 is equal to X21. So that kind of, so all on above diagonal, below diagonal, it's symmetric. So that diagonal is the ridge of that particular Z transpose Z correlation matrix. The diagonal is the ridge of that matrix. And since we use lambda to add to that ridge, we call it ridge regression. All right, we come back here and we see why the reason why 0.95 has so little standard error. X3 is still not reliable, but not as bad as standard error of regular least square coefficients.